Today's lesson is going to focus on the relationship between mass and moles. Towards the end of this lesson, we're also going to bring back the concepts of atoms and molecules. In our first lesson, we looked at the definition of the mole, and we used that definition to determine the numbers of atoms or molecules of different substances. However, it's much more useful for us to discuss substances by their masses. They are much more easily measured by their masses than by counting out atoms or molecules, which we know is actually impossible for us to do on our own. So therefore, we have to establish a relationship between mass and moles. In order to do this, we have to look at the periodic table and the masses of our elements on the periodic table. So we know that all of the masses on the periodic table are represented by a unit of AMU. We saw that in our first unit when we calculated average atomic mass. And we know that these units refer to atomic mass units. But we're now going to look at those masses a little differently. Now that we understand the concept of the mole, those masses on the periodic table actually represent the mass of 1 mole of that element. And remember that 1 mole means 6.02 times 10 to the 23 atoms of each of those elements. So for example, if we look at iron, the mass on the periodic table for iron is 55.65. And previously we would have said 55.65 AMU, atomic mass units. Now we're going to call those masses molar masses, and we're going to put a new unit on of grams per mole. So what this means is that if I had 1 mole, which we know is 6.02 times 10 to the 23 atoms of iron, that mole sample would weigh 55.65 grams. And this is going to be a much more useful way for us to refer to amounts and samples of our elements or of our compounds. For any compound that you have, the molar masses are summative. So you would take all of these molar masses of elements and you would simply add them up. So let's practice calculating atomic mass with a few examples here. The formula that we use, the symbol that we use for molar mass is a scripted M. Okay, so cursive M if you want to call it that, or scripted M, or you can use 2 capital M's for molar mass. Okay, do not use a lowercase m, do not use 1 uppercase capital M. Okay, those units or those symbols mean something different. So if we wanted to figure out the molar mass of barium, barium is just simply an element on the periodic table. We write the symbol for molar mass, and you have to put the formula for your substance in brackets beside it. That way you're just communicating what you're solving for, but the formula becomes very, very important now. You just go to the periodic table and you look up the molar mass of barium, which is 137.33, and we now use the unit of grams per mole. So if I had 1 mole of barium, it would weigh 137.33 grams. For oxygen gas, we know that oxygen is one of our diatomic elements and has a formula of O2. So we go to the periodic table, we notice that 1 oxygen element would weigh 16 grams per mole, but we have 2 atoms based on the formula. So we add those up. Molar masses are summative. And then we get an answer of 32.00. Remember significant figures here, we're adding everything. So we need to represent 2 decimal places. And we put on a new unit now of grams per mole. If we want to calculate the molar mass of calcium fluoride, we write out the symbol for molar mass. And this is where, again, nomenclature is so important, because if you have the wrong chemical formula, you are going to calculate the molar masses incorrectly. Calcium has a charge of 2, fluorine has a charge of 1. We do the crisscross rule and we get CaF2. Now, we have 2 different elements, but it doesn't matter. Molar masses are summative. We add them up. We have 1 atom of calcium in that formula. A calcium weighs 40.08 grams per mole. We're going to add on the fluorine atoms. We have 2 fluorine atoms, and each fluorine weighs 19 grams per mole. So we calculate all of that together, and we get an answer of 78.08 grams per mole. The last one is aluminum nitrate. So aluminum nitrate, again, aluminum has a charge of +3, nitrate's a polyatomic ion, charge of -1. And we're going to come up with the symbol for molar mass, scripted M, and the formula for aluminum nitrate, which would be Al bracket NO3 bracket 3. The 3 outside of the nitrate applies to everything inside. And again, very important that you get the right formula when you're calculating molar masses. So an aluminum weighs 26.98 grams per mole. And then there's different ways that you could calculate the molar mass here of the rest of the formula. What I tend to do is I tend to calculate what an NO3 would weigh, and then I would multiply it by whatever subscript is outside of the brackets. You can also expand it. So if you wanted to expand it, there are 3 nitrogens. So we can add on 3 times the molar mass of nitrogen, which is 1401 grams per mole. And then there are 9 oxygens. Remember, we're multiplying that. So we're going to add on 9 times 16 grams per mole. And then we're going to add everything together. And we get an answer here of 213.01 grams per mole. So molar masses are easy to calculate, but if you don't have the right chemical formula, you're not going to get them right. So make sure that you review nomenclature if you need to. We're going to have you stop the video right now and go into Google Classroom. You'll see a practice problems doc and complete number 24. So just some practice on molar masses before you start the next section of the lesson. Now that we understand that the periodic table represents exactly 1 mole of a substance, we need a relationship to help us determine the masses of compounds when we don't have 1 mole. And almost never in the lab will we have exactly 1 mole of a substance. We might have a little bit more, a little bit less, or maybe a lot more, a lot less. So we need a relationship. So the formula that we use is that moles is equal to the actual mass, this is a lowercase m, divided by the molar mass of our substance. So just a recap of these symbols, little n is mole, unit is MOL, scripted M is molar mass, unit is grams per mole, comes from the periodic table. They'll never give you molar mass because they can assume that you will calculate it yourself. And lowercase m is the actual mass, again, for times when we don't have 1 mole of substance. So let's do some practice problems here, calculating masses and moles when we don't have exactly 1 mole of a substance. So here it says to calculate the number of moles in a 12.5 gram sample of sodium nitrate. So I know that my actual mass is 12.5 grams. Sorry, that should say equals. And they don't tell me the molar mass of sodium nitrate. They want us to calculate moles, which is lowercase m, and they don't give us molar mass. And they never will because they know that you can do this. So make sure that you have the correct formula for sodium nitrate. Each of those have a charge of 1. And then you can calculate the molar mass of sodium nitrate off on your own. You should get a value of 85 grams per mole. And then you can set up your mole calculation. So we're going to solve for moles here. They're saying calculate the number of moles. And we know we don't have 1 mole of sodium nitrate because if I did, it should weigh 85 grams. It weighs much less. So I know that my mole value that I calculate should be less than 1. I'm going to take my actual mass, divide it by my molar mass, sub in my values of 12.5 grams divided by 85 grams per mole. And we're now going to round to proper number of significant figures. And so when I do this calculation, I get an answer in the calculator that is very long, but I'm going to round to 3 significant figures because that is what the measured data gave us. So I'm going to round to 0.147 moles. So this is the data that we would use. Molar masses are constants, right? They never ever change for sodium nitrate. It's always going to be the same molar mass. So unless you have no other measured data, you would use your molar mass significant figures, but anytime they give you measured data in the question, that is what you use to round your final answer. Now we want to do a second example where we're asked to calculate the actual mass of acetic acid. So we'll set up what we know. So we know that the moles of acetic acid are 0.65 mole. So I don't have 1 mole, I have slightly less. And again, they're not going to give you the molar mass, but we can calculate that. And we should know acetic acid is a polyatomic acid or an oxyacid. We'd have hydrogen combined with the acetate ion, which is C2H3O2. When you calculate that molar mass, you're going to get a molar mass value of 60.06 grams per mole. So we understand that our mass, our actual mass here, is going to weigh a little less than that because I don't have a mole. Okay, I have less than a mole. So we know our base formula is that moles equals mass divided by molar mass. I want to solve for the mass. I'm going to take my denominator and I'm going to cross multiply it to the other side. So the mass of acetic acid, and you always tell us what you're solving for in brackets, is equal to moles times the molar mass. We sub this in. That's not an 8, that's a 5. And we multiply by molar mass. Put all of your units in. And now we're going to round to the proper number of significant figures, which is 2, based on our mole value. So the answer that we get to 2 significant figures is 39 grams. Let's try another example where they are asking us for a mass variable. So they're saying, what is the mass of magnesium nitride? So this is lowercase m. We do not know what that is. And then they're telling us that the magnesium nitride contains 2.85 times 10 to the 23 molecules. So remember that molecules is a formula that, or a symbol that we used previously, and that's capital N. So we're going to write that down, 2.85 times 10 to the 23 molecules. So we now need to merge the 2 mole formulas that we have learned. And we'll just jot them down here in the side. So we know that moles is equal to molecules or atoms divided by Avogadro's number. And we now also know that moles can be a mass value. So mass divided by molar mass. I need to solve for mass. And I've been given molecules over here. Now, this common variable between both is moles. So what I'm going to do is I'm going to number my steps because I'm going to have to do 2 different calculations here. And in my first calculation, I have to take the value that they gave me, which is molecules, and I need to calculate moles first, and then I'm going to use that mole value in my second formula. So let's set this up. So moles of magnesium nitride. So again, watch your formulas. Magnesium has a charge of 2. Nitride is just the element nitrogen, charge of -3. So we're going to crisscross and we're going to get Mg3N2. And this is equal to molecules divided by Avogadro's number. So we're going to sub in the molecules, 2.85 times 10 to the 23 molecules, write it all out. And then we divide by Avogadro's number, which is 6.02 times 10 to the 23, and this is a compound, so molecules per mole. We're going to divide that out, and we're going to get a mole value of 0.4734. And there's extra digits in the calculator, but hang on to 4 to 5 decimal places. But don't round yet. This is not the final answer, so we don't round to significant figures just yet. They want us to solve for the mass. So now what we can do is we can take this mole value and we can sub it into our mass formula, rearrange it. We're going to have to cross multiply moles and molar mass, and then we can calculate the actual mass. So sometimes we need to do 2 steps, and sometimes we need to merge the formulas. So we need to calculate the mass of magnesium nitride. We're going to take moles times the molar mass. Again, they will never give you molar mass. They know you can calculate it yourself. So we're going to calculate the number of moles, 0.4734, times the molar mass of magnesium nitride. So stop the video here, take a second, calculate it yourself, and then we'll carry on. So hopefully you calculated a molar mass of 100.95 grams per mole for magnesium nitride. We are now going to round to the number of significant figures, which in the data they gave us was 3. And so we get an answer of 47.8 grams of magnesium nitride. So in our last example, we're going to have you try this on your own. And it's asking, what is the total number of atoms in a 108.3 gram sample of potassium carbonate? So notice that you're first starting with a mass. Okay, so we need to use the formula that incorporates mass, which is moles is equal to mass divided by our molar mass. And then they're asking for the total number of atoms. And just recall that if you're dealing with a compound, you will not be solving for atoms initially. You'll be solving for numbers of molecules. So just recall that this formula here is needed because we need capital N, but that this will be a molecule that we solve for when we use this formula. Then there is one extra step for you to do to get to the total number of atoms. So just review the examples that we've done, and then give us a try. If you're stuck, just come on over and find me and I will help you out. And here's your answer, 2.83 times 10 to the 24 atoms.